Hey everybody, and welcome back to Linear Algebra Online. So the plan for today is to talk about something called change of basis, and this is really important because when you get to a point where you have like a bunch of vector spaces going on and maybe different bases for different vector spaces and stuff, you don't want to always have to kind of go through a very tedious process to rewrite a vector in terms of a new basis. There's like a concrete way to build a matrix which basically does the change of the basis for you. So, if you had like the standard basis for some problem, but you really wanted it in some other orthogonal basis or something that still describes maybe R3 or something, there's actually a concrete way to build a matrix that you can just multiply your vector by, and it'll give you the vector in that new basis. So just to kind of, I guess, put a picture to what I'm saying, like we have two pictures down here that are built out of two different bases, I guess, and they both span R2. We've got U1 and U2 here, and then we've got V1 and V2, and certainly both of those are linearly independent from each other, and they're going to span R2, so you should be able to describe X in terms of U's and in terms of V's, right? And with pictures, it's really not that bad. We can see that X over here is just going to be U1 plus 3U2, and so we have this notation where we can say X in terms of basis B is equal to the vector 3, 1, right? Nope, it's 1, 3. How about that? You go one of these U1s and then you go three of those U2s, right? And so X is 1, 3 in that basis, but, X could also be 5, negative 1 in the standard basis, right? So there's different ways to write X depending on the problem. Over here, we can see that X would equal, what would it be, 6V1 minus V2, right? And so in that kind of notation, we would say X in terms of like script C there is 6, negative 1, right? You go 6 of these V1s, which is actually I hat, right? And then you go minus 1 kind of along that light blue line, which is minus V2. So what we're talking about is we want to build matrices that can do this for us rather than having to like draw a picture or do all that sort of stuff. So there's a way I'm going to show you today to do this actually pretty concretely. Okay, and the other idea that I really want to get here is, so we've done things where we take like the standard basis typically, like E, okay, and we can convert it to, some base B and then E to some base C, and then what we really want to do is, instead of always having to go back to that standard basis, we want to have a way to go back and forth between B and C, let's say. So we really want a matrix that converts between any two arbitrary bases, okay? And there actually is a notation for this. The way we would write this is, actually let's do it this way. So there's some matrix P, and we actually do this weird notation where we do like a backwards arrow kind of looking thing. But basically what you want to think of this as is a change of basis matrix, which is going to send something that's written in B to the same thing but written in C, okay? So if that matrix operates on X written in B, that is going to pump out X written in C. Okay, that looks like an E, but I'm horrible at writing script C, so we're just going to write a normal C. So that's kind of the idea. It's like no matter what bases I have, we want to be able to make this matrix so that we can, pop it on this vector, and it sends the vector written in B to the same vector, but now written in C, okay? And these right here, these U1s, U2s, V1s, V2s, those are actually the exact same U's and V's from over here. And what I kind of want to do is I want to work through a little example to kind of build up how this matrix actually works. So it's easier to see with some numbers, I think. So to start off, just notice U1, which is my negative 1, 2 here. This thing equals 3 of 1, 0, which is V1, plus 2, 1, 1, which you could get with just like, matrix operations, like like set up a 2 by 3 matrix and figure that out. And so it's saying that U1 is negative 3 V1 plus 2 V2, okay? And likewise, if we do the same kind of thing for U2, okay? I'm not going to go through all of it this time. I'm going to write, you get 3V1 minus V2. And you could do the same thing. You can make a matrix to get that. So a change of basis, okay, literally could always be done this way. You could always just go, all right, x equals, we saw that it was U1 plus 3 U2. I think that's correct, right? Yeah. So in terms of U, x was U1 plus 3 U2. But now I have a representation of U1 and U2 in terms of V's, right? So what I can just basically do is I can pop in, just literally like substitute. U1 is minus 3V1 plus 2V2, right? And then U2 is, where is it? 3V1 minus V2. And so then you can like multiply, combine like terms, and you're going to get that x is 6V1 minus V2, which shouldn't be a surprise because that's exactly what we saw over here. And that does it. That actually is doing the change of basis thing that I'm talking about. Like I just did it with a bunch of linear combinations and da-da-da-da-da. So the nice thing is that this process is not something you have to do every time. You can actually speed this whole thing up with matrix operations. So this is basically what I just did. If we have two bases, okay, for some vector space, and we have an n by n matrix whose columns are the coordinate vectors, the n by n matrix, where the columns are the coordinate vectors u1. So writing these basis vectors in terms of these ones, okay, u1 in terms of these, u2 in terms of these, u3, right, all the way up. If you just build a matrix where those are the columns, that will actually send you, that will be the matrix that I was talking about of, here, that if you apply it to a vector written in the original basis, it'll pop you over into a vector written in that same vector written in the other basis, okay? Hence we've changed basis, okay? So if you take a look at what we did here, we had u1 is minus 3v1 plus 2v2, and u2 is 3v1 minus v2. So writing the matrix P that sends B to C would just be, this would be equal to, the columns need to be these things, okay? It needs to be minus 3v1 plus 2v2, and then 3v1 minus 1v2. So this is just u1 written in terms of the basis C, and u2 written in terms of basis C. And I promise you, if you multiply this by the vector x written in terms of B, right, which is this guy right here, 1, 3, if you do that, you're going to get 6, negative 1. It's gonna happen. Really, because it's just the matrix summarization of what we just did here. It just does that, okay? And there's a nice other benefit here, because if this matrix sends you from B to C, it's not surprising that the inverse would go backwards. So P inverse, let's do it this way. P that sends B to C this whole thing, there we go, -1, would equal P, B, C to B, okay? And this picture just kind of sums up what we were just saying. Like, you could take any vector, you can write it in terms of some arbitrary basis C, and you can do that another one in terms of B. And if you just build this matrix where these columns are built out of taking like B's basis vectors and writing them in terms of the other one, and then you just multiply, right? You can kind of go from B to C, and then the inverse here will just go from C back to B, which is a really nice thing. So, so it's a much quicker way to do this rather than going through this kind of thing every time. So this was a problem that we did a ways back when I was first introducing the idea of like coordinate vectors. And we did it where, this is like an orthogonality unit. And basically we did it where we did all these like dot products and things. And then we talked about how we could write W in terms of the basis that's built out of these vectors right here. And in that problem we found, so we did things where it's like, okay, the C1 equals 2 plus 2 minus 3 over 4 plus 1 plus 1, which is equal to a 6. And that 6 is what went in when we write W in terms of the new basis here. That was how we got this one, poorly written there, this 1, 6 up here, and then we did the same for C2, and we popped that in, and then we did C3, and we popped that in, and we got 5 halves and 2/3. And just to kind of show you that this change of basis thing works, okay, what I want to do is make a matrix. So I'm going to make P. Whoops, sorry. I'm going to make P that sends E to B. Okay, E is going to be like the standard matrix, and then what I'm going to do is I'm going to apply that matrix to the vector 1, 2, 3, right? Because that is W written in terms of the standard basis, right? Just 1 I hat, 2 j hats, 3 k hats. And what we should have, right, hopefully it should equal 1, 6, 5 halves, 2/3. Okay, and to do this, we just need to do this thing where we write the basis vectors of the standard basis in terms of these new orthogonal basis vectors, okay? So what we basically need to do, right, is I want like I hat, 1, 0, 0, to be written in terms of some combination of V1, V2, and V3. And so we just do a matrix, right? We just do RREF of 2, 0, 1, 1, because we're just augmenting it with I hat, 1, 1, negative 1, 0, and then negative 1, 1, 1, 0. And if you do that, you would get this. So you can see basically that A here needs to equal 1/3, B is 0, and C is 1/3. So in this matrix P, that's going to send the standard basis to B, okay? That just means that if I write I hat in terms of V1, V2, V3, I need 1/3 of V1, 1/3 of V3, and none of V2. So what I put in my first column is that 1/3, 0, 1/3. And then you just keep doing that. So instead of this RREF, you would do 0, 1, 0, and you're going to get something. I can just tell you what it is because I did it. You're going to get a 6, and then a half, and then negative 1/3. And then you do the same thing. Now you do 0, 0, 1, and you RREF that one, and you're going to get negative a 6, 1/2, and a third. And then, I promise you, okay, if you do P E to B, so that matrix up here, times by 1, 2, 3, right, which is my vector W written in terms of E hat, or the standard basis E, sorry. You should check this, just 100% believe me, but I promise you, it really will equal 1, 6, 5 halves, 2 thirds. So what that has done for us is it's changed the representation of W into a new, based on new basis vectors now. And this was like the picture that went along with that. So it's kind of a neat connection to something we did before. So you can do it this way where we did all these dot products, but honestly, I think this is easier. And when we did this, I almost thought like maybe I'll just show you this way, but I'd rather not complicate it when I was teaching you for the first time. So this is kind of how I typically do these things, is I would just do this, get my basis vector from my original space in terms of my bases that I'm moving into, and then make this matrix, and then just do that computation out. So, yeah, that's just kind of showing you how it actually works. And so really what I want to do now is I want to just sort of show you other ways to do this. So what we have here is the vector space M 2 by 2, so these 2 by 2 real value matrices. And script B is the basis E11, E21, E12. This thing, I don't think I've really talked about it yet, but here, I'll put it over here. So E11 is just a 1 in the 1, 1 spot, and then zeros elsewhere. E21 would be a 1 in the 2, 1 spot, which is actually down here, and then 0, 0, 0. And so on like that. I think you could figure out the rest of them there. And then C is the basis A, B, C, D, which is just given by this, okay? And I want to find the change of basis matrix, and I want to verify that P that sends B to C, acting on B, really does send it to C, okay? And this is the X, the vector that I'm working with, okay? So, there's a cool little trick that we can do here, all right? So we can write B, like the matrix that sends B to the standard basis and C to the standard basis really quickly, because literally we can just look at my my like basis B or C and just copy it into a matrix, right? So what I mean by that is this one would just equal literally E11, just written as a column vector, so 1, 0, 0, 0. And then E21, written as a column vector, so 0, 0, 1, 0. And then E12, so 0, 1, 0, 0. And then last but not least, 0, 0, 0, 1. So that's like really easy to do, right? And then we can do the same thing for this. This one would just be 1, 0, 0, 0. That's just A written as a column vector. 1, 1, 0, 0, B, 1, 1, 1, 0, C, 1, 1, 1, 1, D. So this is kind of the cool trick. If you want to go from B to C, right, this was really easy to do. So what we could actually just do is use inverses, right? We can go and to do B to C, it's equivalent to this, B to E and then E to C, right? Well, we just talked about how the inverse of this one, right, would be P that sends E to C now. So if you just do a matrix multiplication of P that sends C to E inverse, right, multiplied by P that sends B to E, right? If you do that matrix multiplication, it will be equivalent to sending B to C, right? Because it'll switch this around. So you'll go B to E, E to, and you'll be in E, right? And then you'll go to C. So it's really a shortcut almost. It looks like more complicated, but it's actually quicker. And so that's actually a fast way to do this whole change of basis thing. So what you can do is, and you just use a computer to help you do all this, but 0, 0, 1, 0, 0, 0, 0, 1. So this matrix needs to be inverted, right? And if we pop that onto 1, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 0, 0, 1, it really will be equivalent to this P that sends B to C, okay? So now if you started and you did this matrix multiplication and operated on a vector written in B, it will send it to C, okay? And they actually, in this problem, there's a nice, it's pretty nice to write X in terms of B. So if you think about these are your basis vectors for B. It's probably not that hard to see that let's see, what color do I want to do? I don't know. I'm going to do orange. X written in terms of B is just going to be 1, and then it would be a 3, right? Because they basically flipped these two on you. So you would end up flipping these two. 1, 3, 2, 4. You should check it just to make sure. But now, if you just pop that over here, 1, 3, 2, 4, and if you just go and do out, I mean, you definitely just want to use a calculator, a computer, or something to do this, but you would, just type all this in, hit enter, and it's going to literally just give you -1, -1, -1, 4. And that right there is X written in terms of C, okay? And you can kind of see it if you do -1 of these, -1 of these, -1 of these, plus 4 of these. I guarantee you're going to get that, which is kind of cool. So this is sort of it looks like a lot of work, but a lot of it's just done on a computer. But this is a fast way to kind of compute these change of basis matrices. It's definitely faster than doing this thing. And it really is doing that thing. It's just doing it in kind of a clever way. So there's one more way that we can actually do this, and it's going back to just how we did inverses with Gauss-Jordan elimination. And basically what I mean by that is we did these problems where we augmented like A with the identity matrix, right? And then if we do an RAF thing, right, we would switch kind of the placement of the identity, and what's over here is now the inverse. The reason that works is basically it's like this matrix is saying A times something, right, like capital X, because it's a matrix, let's say, needs to equal the identity. And if you solve that out, right, the X will be the inverse, right? And so when we solve one of these matrices with RAF, we are solving, when we look at what's on the other side of augmented is the solution. So we're getting the inverse that way. So one way you can do this is you can basically take, so if you have B is described by this basis, C is described by this basis, you can do U1 written in terms of the standard basis, okay? So basically just copy it in. V1 written in terms of standard basis, again, pretty easy to do. Then you can just, if you want to go from B, you want to get B to C, you just do C over here and B over here, and you just augment it. It's just like this. And when you do that Gauss-Jordan elimination, then you're going to get an identity, and you're going to get what you wanted right there, okay? So just to kind of show you this in action, because you might like doing it this way, I want to find the change of basis matrix that sends B to C, and then also C to B. That's just the inverse, right? And my bases are the standard basis for the polynomial quadratic space, and then this basis for the same space. And this is my coordinate vector, okay? And I was asked to find that in terms of the basis C. Okay, so this stuff is pretty quick here. So 1, plus x is the vector 1, 1, 0. And that's basically all I'm going to have to use to do this kind of stuff. And I'll just make a matrix, okay? It's going to be a big matrix, but I'm just going to let a computer take over. I'm going to put 1, 1, 0 in there in the first spot. So this matrix is like a, it's my C augmented with B thing, because that'll be equivalent to sending B to C, my change basis. So I got 1, 1, 0, right, from that. Then I got 0, 1, 1, 0, 1, 1, and then 1, 0, 1. And then I'm going to just augment that with this basis, okay, which happens to also be actually the identity, which is just kind of a coincidence. You have 1, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1. Definitely does not have to be that simple. There's other quadratic bases that would have worked here too, and you just put them in. But then, if you just go and you RREF this thing, okay, you're going to get this. And that's basically it. So this thing over here, this part is P that sends B to C. I'm very bad at drawing arrows backwards. And then what you can do is you can test this, right? And if I want to send, if I want this vector written in terms of C, right, I just start by writing in terms of B, and I can multiply it here, this by that thing I just talked about, and it will give me P in terms of C. So that is what I'm talking about there. This is my P that sends B to C, and then this is just X written in terms of B, right? And then this was now going to be X in terms of C. So a few different ways to do this concept. You can either do these big augmented matrices and do RF there, or you can do this kind of thing where you just do a chain of multiplications. Or you can kind of go, in my opinion, the kind of a slower way, but still will work. Basically making U1 here as a column in terms of the other one, and so on like that. And then this is a really important thing to remember, that the inverse of the B to C is going to be a C to B, so you can go back and forth. Very important thing. There's a lot of problems, if I use this picture for a second, you might have switched over to here, and you want this space now for some reason. So if you didn't know this trick, you'd have to go back, right, and then back here. But now we have a way to go boom, boom, right? It's way quicker computationally than doing a lot of back and forth to the original space. And a lot of times this is the standard basis. So you can switch back and forth between any arbitrary ones, which is really useful.